Good morning, everyone. My name is Tamoghna Ojha. I am a ERCM postdoctoral researcher in the Institute for Informatics and Telematics in the National Research Council of Italy. Today, I'll be presenting my recent work on energy balancing in peer-to-peer wireless power transfer. So here we are talking about a futuristic solution where we envision that we'll be able to share energy among the mobile devices from one mobile device to another mobile devices uh, with as the as we are able to share mobile data or images from one mobile to another mobile. So this is the futuristic scenario what we envision in this problem. So so the wireless power transfer technology that we are talking about here is a technology to replenish the mobile device's battery. So, and here we specifically talking about the peer-to-peer version, where we are talking about mobile-to-mobile energy transfer, which gives us a lot of flexibility because we can share energy with mobility. So there are some already uh, in standards for this kind of energy transfer between mobiles called Qi or QI. So this kind of standard is found in the high-end mobile devices that are currently in use nowadays. So some of the energy sources that can be recharged with the mobile phones are obviously the mobile phones, and mostly that are in use are like wireless charging pads or mobile charging vehicles. So uh, I'm talking about a scenario like this where there are like n number of locations, and in these n locations there are m number of devices are randomly distributed. So in each scenario, like in each location, there are devices who can provide energy and there are devices who can receive energy. But the number of these devices can be different. Also, this kind of energy transfer is comes with energy loss. So typically we lose around 20% of the energy that is transferred. So the transfer energy and the received energy that is received is less than 20% less than the transferred energy. So we should be careful about who should be transferring energy to which one. So we should be carefully selecting the peers, and this is the problem I'll be talking about. So energy balancing is one state of this kind of energy transfer, where we envision that the ideal energy level of the nodes will be equal, but with energy loss in picture, will not be able to reach that level. But why we do energy balancing is because we want that the nodes to have a kind of extended lifetime. So the nodes who are losing energy, they can get energy from the other nodes who are having more energy, and they can share it, and they can, in a way, extend the functional lifetime of the network. But there are three more different challenges associated with it. One is the varying amount of energy loss. So the amount of energy transfer is directly related to the amount of energy loss. So the more energy we transfer, more energy will be lost. So we should be careful about how much energy we are transferring. Also, this kind of energy transfer is uncertain due to the uncertain meeting duration of these peers. So due to mobility, these peers can move away at different times. So we should be careful about the duration of energy transfer. And also to get a good kind of energy balance, we need to have a low variance of the energy status of the nodes among the network. So the existing works in terms of energy in user engagement and energy sharing, they try to use all nodes or every opportunities of the node. So which is not required because we'll lose a lot of energy. So that is kind of a non-optimized solution, and it generates higher energy loss. And also the user mobility point is not considered in the existing works. So we have a opportunity to carefully select the nodes with respect to their mobility. And so based on that, we devise two solutions actually. We first devise only pointing based on the mobility solution. We call a Mobi Web. So a mobility aware solution where we explore the mobility of the devices. We use mobility prediction using order K Markov predictor, and we select the devices based on this information from the mobility predictor. So the goal is to maximize the average network energy such that the energy loss is minimized, as well as get a minimized energy variation distance among the population. So I'm not going into the details of this work. So in the next work, what we did is we also leverage the social information. Why? Because social information actually influences human mobility. It was already researched in some of the works earlier, and based on that, so we consider two types of social information that is affecting the mobility of the users. So as our concern is with mobility of the users based on with fear selection, so we try to explore this information and see that if it can improve the peer-to-peer power transfer or not. So we consider two dimensions of the social information. One is social context. So it defines that user's preference for visiting different category of locations. So there can be, as I said already, that there can be a number of different locations. So those can be with different categories. So the user will have different priority for visiting those locations. So we consider this information. And we also consider social information, social relations. So that is the user's social friends present on that location. This also can affect the user's mobility of moving from one location to another location. So based on these two information, so our scenario is like that. So where we have considered three dimensions. So first is the social context domain. So here we see that each user has different location attachment value. So we'll see how we can calculate the location attachment. Then we see the social relations domain. So these users who are present over there have different social relations that is shown in the social graph here. And also we have to be careful about the battery power domain. So that is with their the current battery status, who is want to receive energy or who want to share energy. So next, we compute the social context. So first, we compute an average stay location of the users in each location. And based on that value, we compute a simple location attachment value of the users. And based on the location attachment value and the energy status, we devise a selectivity factor to select the nodes, like which pair should be selected with which pair. So we select based on the value of the selectivity factor. So now incorporating the social relations in the framework. So we first take into consideration the social ages between the users. And based on the number of ages, we compute the average social attachment of the users. And then we add this into our existing formula of selectivity factor. So now based on this information, so when we have the selectivity factor information, so we choose it to select the pairs of the users who will be transferring energy from one to another. So we first compute the average energy balance level, that is our target. But with loss, we will not be reaching average value of the network's total energy. So with loss, this value is different. So it is already calculated in the previous another work. So we call this value as E star. So we start with a node who is with energy value close to E star's value, and then we select a suitable pair from the available nodes of the network. So now these two nodes are transferring energy for peer-to-peer energy transfer, and then we move to select next set of pairs. So to evaluate this, we chose like 100 nodes randomly distributed in 5 different locations, where the stay duration of the nodes is also random, like 10 to 30 minutes. And then after this time, they choose another location randomly and move to this location with a random stay duration. So the overall energy distribution of the nodes initial distribution is also random between 0 to 100. Like 100 means it's fully recharged, and 0 is with no value or no energy level. So we consider a charging rate of 0.5, that is like a charger with 7.5 watt hour capacity. This is quite mid-level charger available in the market. So in the market, there are like 12 watt hour and 15 watt hour charges also. And we consider a 20% energy loss. So to compare our work, we use some of the benchmarks where nodes also take share energy among themselves, but without considering mobility, or they don't consider the amount of energy transfer. Uh, they just share their energy and try to get an average energy level of both those two nodes without considering the energy balance level. So we select we measure the performance of total network energy, which will give us an estimate of how the energy loss is there. So if we have less energy loss, then it's better. And then we measure the total energy variation distance. So if it is less, then it's better for energy distribution. And we also check the number of peer-to-peer meetings and number of nodes that reach energy balance level. This will also give us an estimate of the how good is the quality of energy balance. So we see that first we check that in terms of social context and relations, if it is giving us some improvement in terms of energy loss or energy variation distance or not. So we check that it's giving some benefit. So then we check with our benchmarks. So we see that there are less energy loss and the energy variation distance is also minimized in our proposed method. And we also see that higher number of P2P meetings were enforced in our method. Also, a good number of nodes that reach energy balance level compared to the benchmark. So overall, here we explore realistic and more fine-grained P2P modeling, energy transfer modeling compared to the existing works. And we leverage mobility and social information to better model the peer-to-peer energy transfer. And so we results show that from the results, we see that the energy balance quality was also better compared to the existing works. So in the future, so based on this work, we also continued to explore more domains. So we explored the domain of device health and how to mitigate the device battery health with peer-to-peer energy transfer. And we also checked with heterogeneous devices how to control peer-to-peer energy transfer. And some more works can be also done with more fine-grained energy consumption model and more fine-grained mobility model, and considering those in modeling the energy transfer of the nodes. So in this work, we presented the network dynamics part of peer-to-peer energy transfer. In our other works, we worked on the device dynamics part. So if you are interested, you can check these works. And these are some of the references. So thank you so much for your time. And if you have any questions, you can reach out to my website or my email ID for more questions. And thank you so much.